So thank you very much, and thank you for organizing this this program for half year. And so I offered this talk because the title of your semester is Anomalous. I hear back my voice somehow. So anyway, so the title of the program is Anomalous Diffusion, and there is so much in anomalous diffusion that. So as if you look at this program, so there are really from, I don't know, computer science and also statistics, and all somehow related to some kind of anomalous diffusion. So what I want to do now is to speak about one single aspect, that's how in physics, as far as I know, how it came up, and so these problems of anomalous diffusion, how it came up, what the physical background is, to give you some physics sort of argument. So the great part of my talk will not be rigorous mathematics, and actually I will not give you much of technically speaking, of rigorous mathematics, more like physical problems and arguments coming from physics, why it is difficult, why is it relevant, and a few things which can be done mathematically, but very, very little is doable mathematically. I mean, properly and with that rigor you would love. So how this anomalous diffusion problem, at least what I know about this, and probably others would have other stories about this. So in the late 60s, actually between 1967 to the early 70s, there is I don't know whether 71 maybe is the last paper. There was a series of papers by two physicists, Alder and Wainwright. And it started with the following problem, and a very surprising fact, actually. So they studied diffusion, and actually numerically. At the time, of course, computers were not that strong, but people were clever. Okay? They could do quite good numerics. So they studied diffusion in a gas in two and three dimensions of hard cores, non-overlapping hard cores, distributed randomly. Of course, we know that there are problems here, how to mathematically clearly define what would be the good hardcore Poisson, but with hardcore and so on. But don't worry about that. So it can be somehow at the physics or at the simulation level, it can be done. So quite big. I didn't look up now the papers, what it meant big, but big at the time. I don't know, a few hundred particles, or maybe around 1,000 particles. Started from kind of equilibrium. We can guess easily what the stationary state in the infinitely extended problem would be. That would be this kind of hardcore gas plus independent, identically distributed Gaussian velocities, say, and follow the trajectory, and they move according to the laws of what we learned from Newton. So they collide elastically, and follow the trajectory of one of them. These are not fixed particles; they all move. Right? They all move, they collide, they interact between them, and follow the trajectory of one particle. Of course, this is the classical problem of particle of tracer diffusion in a gas. And what they noticed, and I will ask you how many of you knew about this, because this is a very, very interesting thing. What they noticed was the following, that in dimension 2, what do you expect? What do you expect? Mathematically, okay, in today's terms. So you follow for a long time, in an extended system, the trajectory of one particle in such sort of a gas, and you have random initial conditions. That's what you expect, isn't it? Yeah. So the surprise is the following, that in dimension 3 and more, or 3, of course, they didn't more than 3. In dimension 3, indeed, of course, they don't speak about CLT, they speak about velocity autocorrelation function. They are interested in the variance of the displacement in time t, and assuming stationarity and this Green-Kubow formula, which I will put on the blackboard shortly, you can infer how the variance at time t of the displacement would look from the velocity autocorrelation. From the variance of the displacement is the integral of the velocity autocorrelation function. That's an easy computation, right? And what they noticed that in dimension, let me denote by CT, the velocity autocorrelation, let me use notation as physicists love to use. So this is mean expected value or covariance of velocity at time t and at time t at the time 0 and time t. So what they notice is that in dimension 3, this would decay like t to the minus 3/2. And in dimension 2, this would decay like t to the minus 2/2. So there is some sort of argument that in dimension d it would decay like t to the minus d, which is not integrable. So the integral of this CT, if you do some very short computation, the integral of this CT would give you the asymptotic variance in the central limit theorem we expect. Right? In 3 and more dimensions, so if we trust this, then in 3 and more dimensions you would expect diffusive behavior, but not in 2 dimensions. Now, how accurate this t to the minus 1 is, we will see at the end, or later we will see how accurate it is. But nevertheless, it's not integrable, which somehow forecasts that there is a problem with diffusivity, with diffusion. So that the diffusion is faster than what you would expect as a question.
Will they be able to see a log factor in this?
We'll see. We'll see. So that's the problem. That's the problem that in 2-dimensional, of course, this is is a sort of idealization with hardcore and so on. But I don't think it's that it changes much. And of course, you may say that in 1970 maybe the computing power was not that strong, and indeed you expect some logarithmic stories here. So at least in the displacement, some logarithmic correction in the variance logarithmic correction to the linear in time, and maybe that was not so at the time they couldn't measure it quite well. But these guys not only measured, they also had ideas about why this happens. And that's what I want to tell you. Okay, so let me just ask: is there anyone here who knew about this older Wainwright story? No? And why? Why? So I will try to give you the argument reconstructed in my terms, because if you read these physics papers, it's not so easy to understand. But of course, it's not because the ideas are not good, because the way of writing it down is not so clear for us. But what we will see is what I'm telling you is ideas from this older and Wainwright, and the later, or about the same time, but towards the end of this interval, there is another paper. I would quote here Forster and Nelson and Stephen, 1970. Just for side information for those who know the person I will mention. So this guy older is an uncle of Jeff Staves, or maybe great uncle of Jeff, for those who know. Good. Anyway, I learned it from Jeff once when I spoke with him about this. Anyway, so the argument would be the following. What I'm going to tell you is a scaling argument, non-rigorous. There are ideas here. I think what I want, so my goal is that to make you appreciate ideas even if they are not rigorous. And of course, our mathematicians' goal would be to make some elements of it more rigorous than it is, but it will make sense. Okay, so what we are looking at is a motion random. Okay, I will do it a bit more general. This looks like deterministic motion. I do it a little bit more general. I allow some randomness coming in along the dynamics as well. Right, so let this be a random trajectory in RT. Right? Let's call this is the tracer particle motion. Now, usually I will assume stationary increments in our probabilistic terms. right? Stationary increment. So I will write it, usually what we do, we write it as we separate a martingale part. Of course, the physicist will never say this. And what we call a compensator, which plus, this is just definition, if you wish, of the right-hand side of let me call it V. This V is about the same V as that one. Right? So this would be a martingale part. This is nothing else, but assume that you can subtract an integral, which makes it a martingale. And usually you can do that. Usually you can do that. And I'm looking for super-diffusivity. I'm looking for super-diffusivity. So this is the martingale is the compensator. And assume something, namely that there is a background, there is some randomness in the background. So the background, in that case, the gas in the background. So I follow one particle, but there is an environment in which it moves. The environment, I'll let me call the environment background. In the background, there is a velocity field. So there is a random field UTX, so which is changes, might have a joint dynamics with that guy. And it's a field, it's a vector field, and it's some sort of local velocity field at the position x at time t. Right? So particles move there. When my tech particle arrives at a point, there is some local velocity there, and it picks up momentum from there. Right? And let me say that this Vt, that Vt from there, is be equal to u of t and xt. This is a simplification because it's not the case that it picks up the velocity field from there, but it picks up something from there. I could put here an epsilon or something, but I don't do that. Right? So, question? Stop me because it's vague what I'm speaking about, so just stop me, right? So that's my velocity field is given by that. And I think about joint dynamics. The joint dynamics, so T maps xt ut. Right, so this is you may call it in today's terms, maybe you would call it a random walk in dynamic random environment, something like that. Right? Okay, what else I need? And I make an assumption which is important now, because in the scaling it will matter. If I don't make it, then I might get a different type of scaling limit in the end. Let's assume that everything is isotropic, that all distributions are isotropic, all directions are the same. Good. And I should introduce some things. Namely, I call k px be the expected value, so the covariance of u at 0, 0, and u at t and x. I could make it a matrix. Remember, this u, I'm sorry, this u is the same. Maybe I change this u, script u, right? So the script u is a vector field. I don't care now about the components of this matrix. I just care about the trace. Good. And I also call CT as before. I introduced it already, but let me write it down again. So this is the expectation of V0 VT. Right? I will assume in my arguments that V is stationary, that this is a stationary in time process. I don't assume that U is stationary. It's mind that V is defined like this. V can be stationary even if U is not a stationary process in time. So I don't assume stationarity neither in space nor in time of this field, but I assume stationarity in space of this guy. So as the particle goes around, as time goes on, it feels exactly, stochastically, it feels the same type of things everywhere, as time goes on. Good. So due to stationarity, due to stationarity, of course, I may say that I may say this. Right? Okay. And I still, okay, still have some space here. I denote by E without, not doubly, this is an E, it's a symbol, it's not an expectation. It will be an expectation. B, the expected displacement. I mean the variance of the displacement. By isotropy, the expected value of xt is 0. So this will be the variance of the displacement, right? And I still have to do something. I denote by E tilde. It's almost the same, and actually I will think about them as the same, but they are not quite the same. Integral from 0 to t of vs ds squared. So I still have my martingale decomposition here. So E is the variance of this guy, and E tilde is the variance of that guy. And I'm shooting for super diffusivity. Now this is okay, I didn't say, but this is an L2 martingale of stationary increments. So certainly this behaves diffusively. This guy behaves diffusively. So if there is super diffusivity in the story, then this E and E tilde are of the same order.
Over time, the velocity is in just the position, or?
You see that I allowed some random additional thing here. So if it was fully a deterministic thing, then the two would be equal. But is it clear? So and let me emphasize that these two are not the same, but in case of super diffusivity, they are of the same order, and that's what I'm looking for. Okay. Okay. And I will finish with these introductory things very fast and do some computations. I'm looking for a sponge or eraser or something. Table behind the door. Ah, yeah. Thanks. Okay. And due to stationarity, I do have E tilde t equal twice integral from 0 to t. This is Kubo's formula. T minus s ts. That's just stationarity of, so if I have stationary, it's an elementary computation. Yeah? Which is of the order of, and this sign will appear many times, and I don't exactly know what that means, of that order, something of scaling order, of t times integral from 0 to t cs ds, unless this c behaves somehow very irregularly. This is always the case. Let's assume it behaves regularly enough that this be true. And this is what we call the Green-Kubo formula, or the simple version of the Green-Kubo formula. Good? And now let me, so with these notions, is there any questions? Stop you at any time if it okay, don't try to understand it mathematically. Don't look for epsilons, look for phenomena. Okay? And I'm curious, I want to say something about the scaling order of this guy. Right? Okay, so scaling assumptions. I make some scaling assumptions. The first one is that I assume that xt is of the order t to the mu times log t to some power gamma. To be seen what nu and gamma is. If gamma is 0, nu is 1/2, that's normal diffusion, right? And this is what I will call alpha, because there will be a beta later, alpha t. And my goal is to say something about these new. So more precisely, and of course the physicists will never speak in this language, but what we need is some kind of local limit theorem holds for this guy with that scaling. Yeah, so what I assume actually is that the probability that xt is in, say, dx somewhere is something, say, I write it this way because that's vague enough, alpha t to the minus d times phi alpha t to the minus 1 x dx. So this looks like a local limit theorem with scaling alpha. And about phi, I assume that it's nice, regular. So phi is as it should be. So it's, of course it's positive because it's a density, but it's like that. Good. Yeah. And about so this is one of my scaling assumptions. And of course I want to, okay, when I speak about scaling, I think about something like this. So if I want to say so about the scaling limit, this is something what I have in mind. And about the velocity field, this utx, I also assume something. I assume this might be, okay, this might be somehow mysterious, but it's not so mysterious. That, did I say what kt and x? Did I define k, the correlation? Yeah, there is k. So it's the covariance of the. So I assume that ktx also scales. Assume that ktx scales like some beta t to the minus d times some other function psi beta t to the minus 1 times x. This is not a density function. This is not a limit theorem. It says that at large time and space scales, this covariance behaves asymptotically like this. And this is a reasonable assumption. And about psi, I will also assume some things. I will assume, namely, okay, if you have it like that, then first of all, you notice this psi, let me assume that it's an integrable function in RT. So it has sufficiently fast decay, right? And what I want to say that from here you see immediately that integral ktx dx on RD is constant. Yeah, because if okay, essentially constant. If it was exactly of this form, then it would be constant, which is a kind of conservation of momentum in the problem. So it corresponds to conservation of momentum, that the velocity field is not created. The integral overall of the velocity field is constant. Okay. If it was exactly of this form, then with a change of variable, you just get the constant. So this is just, you see, you have beta to the minus 1 and here beta to the minus 3. Now, as it is here, right? And regularity. Let me not write down the regularity assumptions because it just takes time. About phi, I only assume, so it's a density function. It has it's integrable and it's positive at 0, let's say. So it's like that. And about psi, let me assume that it's an integrable function, absolutely integrable function. It's not an essential thing, but let me assume that because then I can just quote at one point the dominated convergence, right? And what else? And yes, I also assume so not only integrable, but it's integral without the absolute value. Its integral is positive. So the Fourier transform at p equals 0 is positive, right? Let me assume that. And one more assumption. So these are reasonable things. One more assumption, which is also reasonable, in my opinion, is the following, that the beta t, about which I didn't say anything explicit, but b not bigger, so b or capital O of alpha t, which means the following. Okay, I will tell you a few words of explanation why this is reasonable, what I did so far. in the problem with which I started, so the hardcore problem, the hardcore gas problem, what is I have a hardcore gas in equilibrium. I put in an extra particle at the origin, that will be my tagged particle, so it's a kind of palm version with a velocity pointing that way. And otherwise the background is neutral, right? And I ask about the velocity autocorrelation, but this means that I insert in the equilibrium background, I insert something at the origin, an extra velocity, which is broken up and distributed to the other particles as time goes on. And there is a kind of diffusion of the extra velocity which you started with. And what's meant here is that the diffusion of that extra velocity which is put in the system is not faster than the diffusion of the tracer, right? There are examples, in particular in one dimension, when it's faster, but it's reasonable to assume that it's not. Yeah, good. What else?
Like, for when you have the envelope and the media and stuff like that.
I'm not sure I see this, but probably you're right. I don't know. But this is like, so I have my understanding is that there is this extra. So I have a zero velocity field at the beginning. I condition it to have a particle of velocity 1 pointing in that direction at the origin, and time 0. Then the interaction starts, the particle moves around, diffuses, but also this extra velocity is, by collisions, it's distributed among the other, and the other particles also collide between them. So this extra velocity, which was in the system at the beginning, spreads out. Right? I mean, its distribution spreads out. And now I start computation. So these are my input ingredients. And I start to compute on the next. Okay. So I compute CT. CT is the velocity autocorrelation function, right? So I write it here. So this expectation of V at 0 dot V, right? Okay, this is expectation of U00 dot UT. Right? Because V is okay. That's what I assume. Okay, now I cheat. Okay, this is in red. Now I cheat. Right? This is about, so this is a difficult object because U is a random object, XT is a random object. I evaluate U at XT and I take this. It's a difficult object. Nevertheless, I say, okay, let's assume decoupling, that at late time, it's always about late times. At late time, the distribution of this guy is essentially independent of the background thing. It picked up various things on the way, but at late time, that doesn't matter. Of course, this is not true, but okay, no, it's not. Of course, this is true, but it's not easy to prove anything like that. It's very difficult and probably not very much possible to prove. So here I write it like integral on RD of what? Of K Tx dP or P xt in dx. So this is decoupling. Decoupling of the background field from the position. Now I use my scaling assumption. This is also a bit dangerous, not as this is the most dangerous part of the story, right? Now I use my scaling assumption. So this is integral on RD of remember, I assume that this guy I still have on the blackboard. I replace on kt that thing, so I have beta t to the minus the psi beta t minus 1 x. And I have a scaling for this guy as well, and it's up there. It's alpha t to the minus d times phi alpha t to the minus 1 x dx. Now I do something what is absolutely not dangerous and legitimate. Maybe I change some variable here. I change variable here. So what I write is this is equal to alpha t to the minus d integral on RD. I have psi at y, and I have phi at beta t divided by alpha t y dy. Right? What I assumed was that beta is smaller or equal than alpha. It could be much smaller. Then I have convergence to phi at 0, which is assumed to be a positive constant. I could have them equal, then it say, then. Anyway, so what you see here in the limit is a constant. So what you get is this is something like alpha t to the minus d. Right? So the velocity autocorrelation function, if you allow me to do all these dirty things, which I did, then the velocity autocorrelation function is alpha t to minus d. Good? Or of that order. So let's conclude. Let's conclude. Let's see what we have all together, right? We have three components of the argument. One is that ET, that's we call it the variance of the displacement at time t, is alpha t squared, because it was assumed. I assumed that x is scales like alpha. So this is alpha t squared. That's one. This is due to my assumption. Second one I just derived, that Ct is alpha t to the minus d, right? And there is a third one, the green kubo. Which says that E tilde of t, which is about the same as E of t, right, is t times integral, or of the order, t times integral from 0 to t of ts ds. Yeah. This is the variance of the integral of v. V is a stationary process whose correlation function with time difference is ct. Right? Now, if you put these three things together, and let me not do the computations, there are dimension-dependent solutions and one single solution to this problem. One single solution to this problem. I leave it as homework for you. You get in dimension 1. In dimension 1, you will have nu equals 2/3 and gamma equals 0. I mean consistent. You have to find a consistent solution. That means no logarithmic two-thirds scaling. Some of you recognize two-thirds scaling in one dimension. And no logarithmic correction. In 2 dimensions, you want to guess? Somebody wants to guess? You get, so that means that ET squared, so in 1 dimension, EXT squared will be of order time to the 4. In 2 dimensions, the only consistent solution of this problem is nu equals 1/2, gamma equals 1/4, and nothing else. Which tells you that in 2 dimensions, the displacement, the variance of the displacement should be of the order t times log t square root of t. And in 3 and more dimensions, of course, you get nu equals 1/2, gamma equals 0. So standard or normal diffusion. Yeah? Very simple. Very simple, and what is surprising is that the result is absolutely accurate. So in many, many examples we know, or many, we don't know that many examples, but in the examples we really know, this is the scaling. From very, very simple assumptions, from very, how should I say, naive computations. I can give you I can make copy of my handwritten notes, which are better than the blackboards. Okay, so that's the physics argument. It's okay. If you open the papers, you will have difficulties deciphering it, but this is there. This is there. By the way, I have to say that I learned this argument. So this is personal, actually. In 1985, in Oberwolfach from Henk van Beieren. Some of you may know Henk. He's a mathematical physicist, a very, very brilliant mathematical physicist. It's so amazing that I was fascinating all my life since then by this, that one should try to really make mathematics out of it. Right? Is there any question? Because I will turn now to some mathematics from now. No question. Come on. Yeah?
Are there like examples, constructed examples in math where you get this?
That's what I'm turning now to the mathematical examples where indeed the mathematics is there. Or it's not there, but it should be there. So if there is no question about what I told so far, then I go on.
Maybe just an overview of the core of the physical argument, something that has to do with the decoupling of the velocity. And
the decoupling is the shaky part, of course. The core is that you assume some kind of scaling. That's always how physicists think about problems. That there must be, in interesting problems, there must be scaling. And you have to understand what kind of thing and how various things scale maybe in different ways in the physical system. This was alpha and beta. It was reasonable to assume that the diffusion of extra momentum is not faster in 2 and more. Okay, in any dimension, but so that at least that's the restriction. We should restrict ourselves. I will give you a model, one-dimensional model, and this is not the case. But that's a reasonable assumption physically in many ways, many cases. This is the core. And of course, the computation is in each single line. None of the 4 lines of my computations were fully rigorous. But one was really shaky, and the other ones were like, look, probably it can be. So if you try to make a proof out of this, then probably your most difficult point would be the decoupling. That's what I think about, right? And in the cases when there are proofs, it's not done in this way. So you could argue in this way to guess what to expect, that the proof doesn't go this way. Because, yeah. Okay, so can we do something which looks like this? And now, okay, we'll speak about some cases where yes, and I go back many, many years, and I will speak about something about what I spoke in this institute first about 30 some years ago, 31 years ago. And there is one person in the audience who was there at that time. And we're happy to see that. More than happy to see that. Good. Maybe there are two, I don't know. Well, at least one there is. Good. True self-avoiding walk. Or diffusion in more than one dimension. In one dimension. And this is something which absolutely fits into this argumentation, and on the other hand, in a very different way, it was so there are mathematical reasons. So take a random walk on the lattice, on the integer lattice in one dimension, discrete time. Now I will also speak of continuous time. Right? And the rules are the following. When you are here, I don't want to formalize. When you are here at this point, it's nearest neighbor walk. When you are at this point, in the past you had visited this edge a number of times, either way, and you visited that edge a different number of times. Call this one L, call this one R. This depends on the trajectory. This is a function of the past, so it's measurable with respect to the past, right? And you have as ingredient your favorite non-increasing function. Non-increasing, just not constant. Constant is no good. No, a function which is non-increasing, and at least at one value it decreases, right? And your walk does the following. The probability, okay, let me not formalize. The probability of jumping that way or that way will be W of, so that's non-increasing, so that's R minus L divided by W of R minus L plus W of L minus R. And this is the other way, I don't write it down. So what matters is that this is a non-decreasing function, R minus L. That means that the walker is pushed locally towards that part, in that direction where it spent less time in the past. It's pushed away. So in the big picture, it's pushed away from regions much visited in the past. And it's pushed by the gradient of the occupation time measure. It's pushed by the gradient by the negative gradient. So this non-increasing that corresponds to negative gradient. Right? Call this walk x sub n, xn. Right? And if you think a little bit, I will not tell you how this argumentation can be applied to this, but it does, because indeed, wherever it spends some time, it leaves some trace of the past there, and it picks up the past from where it comes back. What do you expect, by the way? Okay, now, of course, I told you what to expect. I told you what to expect. So it is the case that this guy indeed divided by n to the 2/3 obeys the limit theorem. So it's super diffusive, and exactly super diffusive converges to something, let me call it like that, which is essentially not explicitly in the sense of a formula, but the distribution of that guy is characterized. It's interesting. It's not one of these standard things you know about, stable or whatever. Good. So that was, as far as I know, this was the first time such a limit theorem was mathematically rigorously done. The problem comes from physics again, of course. This true self-avoiding walk was first formulated not with local time on edges, but local time on sides. It comes from a paper of Parisi and some collaborators. some 10 years before. This, by the way, this was done in published in 1995 in a paper of mine. But I spoke about this here in this institute when the institute was open. Actually, I think it was just the second program in the DS Newton Institute. Okay. Now this is the one-dimensional. There is another version of this which is done, namely with continuous time. Continuous time, I will not write down formulas, spent on site. Take a continuous time random walk, and in the background, so by the way, the background story, this U, the background field is this occupation time field. So that corresponds to what I call U of T and X, right? Now in the continuous time, you would count the occupation times on sites, and indeed the jumps would be, the jump rates would be a function like this of the gradient of the occupation time on site, right? And the same result was. But not much more. So it's, the result is done and okay, but it's not robust in the sense if you change the model and you define something very similar, but say next to nearest neighbor jumps allowed, then already the proof breaks down. There are some combinatorial elements of the proof which work only for this case, only for this type of case. Now, related to this later, a couple of years later, not many years later, with Wendelin, we constructed the limiting process. So what you expect here as a, okay, the first question you ask once you have a one-dimensional marginal distribution as a limit, whether the limiting process exists. And indeed, what we constructed with Wendelin in 1998 was a limiting process like the scale invariant sort of universal limit process for this object, which we called some name. But anyway, what it looked like was, okay, between quotes, because it doesn't make sense what I write on the blackboard, but it makes sense mathematically as we did it. So it's driven by the negative gradient of its occupation time measure at the actual position. Okay, plus, I'm sorry, my blackboard is not very nice now. Okay, you would expect some randomness here, but I put a question mark because I don't want to speak much about this. So actually, there is no extra randomness put in the system. It looks like a deterministic object, but it's not. Let me not speak more about this here. So due to the very, very strong irregularity of this partial differential, of this, say, partial differential equation, there are no deterministic solutions, and the construction we make is a kind you can interpret as solution of this problem. But anyway, this type of problem, and this would be the scaling limit of the problems, is reasonably well understood now, except the fact that we don't know universality. We are not able to look at a big family of robust family, and we don't have an analytic proof of the convergence. We have a half combinatorial, half analytic, and the combinatorial parts are sensitive to small changes. Let's go to higher dimension. Question?
It's really L and not with a logarithm? It's really the local time itself?
It's the local time. It's the local time, isn't it? Yeah, the local time. So the process, that, if you want the theorem, but let me not spend time because anyway, too much technicalities will be. It does have a local time. It has its occupation time measure. So we prove that the occupation time measure behaves as it should. So it exists, and of course, it's not smooth, so its derivative doesn't make sense. Mm-hmm. But what we construct can be interpreted in a particular way, can be interpreted as a random solution of this partial differential equation. Good. So one dimension is, let me not erase this picture. One dimension is nice and understood. Let's go to higher dimension. In order to go to higher dimensions, I have to, okay, the same problem can be put also in continuous, not on lattice. And in some cases, it's more convenient to speak about the diffusion counterpart. So the diffusion counterpart would be, let me find it. let me, yes. So let me speak about the diffusion story, so the continuous, so on. So now my process xt is on Rd. D could be 2 or 3 or 1, but 1 is, yeah. It has an occupation time measure, so let me call LTA the occupation time measure of this process, so that S between 0 and T is such that XS is in A, right? I need, in order to define my process, this will be the process before the limit. So I want to understand how the scaling limit of the process I define. I need a sort of smoothing function, because this local time, even in higher dimension, even more, or how should I say it, the irregularities, I want to smooth it out somehow. So V is an approximate identity. So V of x is something like, for example, e to the minus x squared, if you wish. It's very important in my story that this V is of positive type. His Fourier transform is positive, non-negative. That's very important. Not physically, that's interesting, by the way, that it's important in the computations, but I will come back to this. I will come back to this, yeah? And let me also allow some initialization of the local time. So L0A, I can start with some measure, which could be a signed measure, from which I start the local time. Good. And the process I'm looking at is dxt equals dbt minus gradient of V convolved with LT at xt dt. You see, this is very much the same as what I spoke about in the discrete setting. Just so so if V was an identity, not an approximate identity, then this would be driven. So you have Brownian noise, and this would be driven by the negative gradient of its occupation time measure. Right? But I have to, in order to make so this stochastic differential equation makes perfectly good sense. If you assume about V sufficient regularity, then this makes perfectly good sense. You have strong solution. Right? And the question is how this guy scales. And again, I could apply to this the non-rigorous argument I gave you before. And what we could prove about this in one dimension, this is exactly, you expect this is exactly in the same class about what was the lattice one. Nevertheless, I'm not able to prove a limit theorem, that sharp limit theorem for this one because of the combinatorial aspects. So because this is not fully local, and on the lattice, that guy was sufficiently local to let me do some tricks, right? So what we can prove about this one, okay, of course we expect that this scales it scales like that in the various dimensions. So that would be a conjecture, if you wish, with Gaussian limit in 3 and more dimensions. I would expect that in one dimension, the scaling limit is the process we constructed with Wendelin, but we are not able to prove it, of course. Yeah, what we can prove is the following. So this is partly, so joint work, this is back in 2012, 11, 12, something like that, with some young people at the time who were my PhD students at the time. So namely, what we could prove was in dimension 2, we could prove that the expected, so that the super-diffusivity, at least, I expect it to be of order t times square root of log t. But what I can prove, what I could prove at the time, or we could prove at the time, that this is larger than, much larger than t times log t. and it's less than, this is trivial essentially, is less than t times log t. And what I expect is that this should be of order t times square root of log t, as I told you, and actually much more. But now, okay, I will comment. I don't know how we stand with time. I'm over time.
No.
What is the time? It's 4. I'm not yet over time. Good. So this was done with Benedek-Valco. And the other result in 3 dimensions, that's a essentially complete result. So in dimension 3, nothing is essentially complete, is indeed a central limit theorem. But with a grain of salt. Take it with a grain of salt. Take both with a grain of salt. I warned you that I add some initialization to the local time. Don't start with fully empty local time. So that was the original problem. Start from 0 and build up local time. But I say, okay, let's initialize. Let's initialize.
In a symmetric way? Isotropic way?
I tell you how. By some miracle, by an absolute miracle, which I can prove, but I must say that I don't deeply understand. And there are so many experts of the words what I will pronounce here around that maybe they will tell me, they will explain me more. By some miracle, this process has a very interesting property. Namely, if you look at the environment is the local time profile, as seen from the position of the particle, and you move around and you look at the process, the environment. This is a process, a field valued process. So you have to build up the. It's not a big deal, but you have to be a bit cautious about how you do it. Then it happens that in 2 and 3, in any dimension actually, and actually don't look at L, sorry. This is what you look at. This is the smooth, so the local time locally regularized. Yeah? Locally regularized local time. It makes sense to ask about its gradient because it's locally regularized. So that's a field, that's a vector field. And you travel around with a particle, you have a vector field around which changes due to 2 things. One is shift because you move with but you also add local time where you are, and it changes by that as well, right? This can be understood well. What happens is that its gradient has a stationary measure, stationary in time measure, and the stationary in time measure will be the gradient of the Gaussian free field. I mean the Gaussian free field regularized locally. And its gradient is a stationary object, it makes sense, right? So that's a stationary, and when I say I initialize with that. So start from an initial field, which is this thing, right? And then start your process. The environment as seen from the random walker, which will be a Markov process in this function space, whose stationary ergodic measure is this one, what I told you. More precisely, this is a stationary and ergodic measure for it, right? In 3 dimensions, it's easier to speak about it because you don't have to take gradient. You may speak about the local time itself, and that will be. So the Gaussian 3-dimensional Gaussian free field as a stationary object and regularized locally, that will be a stationary in time state of the environment as seen from the random walker. And then this is a Gaussian field. You have techniques to apply to so you have the L2 space, which is a graded Hilbert space. You can write down the infinitesimal generator. There are very beautiful things, is creating and annihilating operators coming in, as in quantum field theory or quantum physics, and you can do things. And the central limit theorem is proved using a kind of Kipnis-Varadhan, but a non-reversible version of a Kipnis-Varadhan type of argument. But with this initialization, so it's not the case that you start with whatever initial, for example, empty local time. I can do it with this initialization. Okay, so these are three examples where that kind of scaling argument seems to predict the good values of the scaling. There are other examples. Of course, my time is gone, but there is this random walking random in divergence-free random drift field, which is revived now by some new works. We had just in one sentence. So that's a different kind, but it's related somehow to this. So take a random walking random environment, random diffusion in random environment in d dimensions, but now do the following. Take the Gaussian free field in dimension 2, say, regularize it locally, you get a smooth field of stationary increments. Take the curl of this field, the two-dimensional curl. That means that sometimes it's called perp gradient. I don't like this. So the gradient rotated by 90 degrees. But that's actually the curl, the rotation. So it's the height function. Its rotation is a vector field whose this component is that partial, and this component is negative of that partial, right? So this is a vector field. And start a random walk start a diffusion in random drift field, where this is the random drift field. And in the same paper, we proved the same type of lower and upper bounds for that random walk in random environment. And this got so a revival in the last 1 year as there are 3 papers now, one by Toninelli and co-authors, the other one by Felix Otto and co-authors, and the third one, the most recent one, by Scott Armstrong. And essentially what they do, they improve totally. So they prove our conjecture here. They prove our conjecture. We thought it was our conjecture. It's never the first. You are never the first person who could. It turned out that in the physics literature, this kind of conjectures appeared earlier. Okay, so that was what I wanted to tell you. Take these physics arguments more seriously than usually mathematicians take it, because there is much there. So, of course, no proofs there. Thank you very much.
Can I ask a question? What about if you take your process X, if you add one coordinate, for example, the local time at time t, does it make it Markovian in some sense?
Does it make it?
Markovian. Can you make the process X to be Markovian adding coordinates? Adding information. So you take bigger dimensional process.
Oh, you mean the spatial dimension? D is larger than large.
And then another process, another coordinate, which is related to X, for example, local time maybe at time.
Yeah.
Then is this guy.
Yeah, but the local time is an infinite dimensional object. So it's not just local time where you are, it's the local time profile altogether. Yes, of course, you can make it, if you add sufficiently much, you have it go. For example, I think I was explicit about this, that if you look not at the process, but at the environment as seen by the moving tracer, and the environment means this field. So this is function of time. It will be Markov in time, but it's a field, right? So so that is a Markov process in an infinite dimensional setting, in a function space. So the trade is that you give up finite dimension, you get Markovity, and it helps because you can do with infinite dimensional Markov process, you can do things, but yeah.
So very useful in practice.
No, I don't say that, because this central limit theorem is proved in a functional analytic setting, in that very concrete functional analytic setting, in that Hilbert space with operators and so on and so on. I mean, Hilbert space is the L2 space over this Gaussian free field, gradient of Gaussian free field random object. Yeah.
These examples basically have one particle which creates its own potential
Yeah.
field, right? And
Yeah.
this is what causes the super diffusion. In the hardcore disk model that you started with, where do we see any sort of self-reinforcement?
I tell you. Okay, that this is poetry actually, but nevertheless it makes sense. So namely that the particle has initially a velocity. It's about the velocity autocorrelation. Yeah, you have to integrate the velocity autocorrelation. So it collides with this guy collides with that guy collides with that guy, and so on. And with some chain of recollisions, the particle feels, so recaptures part of its own initial velocity, because initially it gets information about its own past. That's always the problem. The recollisions or chains of recollisions carry information about the past. And carrying information about the past or quantitatively may mean that look, at 100 years later, when you collide with some particle, then a little tiny bit of that initial extra momentum you put in the system is taken up. It's much more complicated. This is a baby version.
For the avoiding walking dimension, what are the tails of this?
Aha. It's e to the minus x cubed. E to the minus x cubed. So the distribution of xt I erased it already. The distribution of the, so it's all, that's an interesting thing which I don't understand, but it's always the case that if you have super diffusion, so if you have to scale with stronger terms, you get tighter distributions in the limit. So faster diffusion, tighter tails of the limiting. This is not a meta statement even, it's just, that's how what I have seen.
And this index 2/3, it also gives you the Hilbert regularity of.
Just this thing of the trajectory, yeah.
Is there any sort of link between this first of avoiding random walk and fractional Brownian motion?
I don't think so.
Any loose?
I don't think so. Okay, but that's my prejudice maybe about fractional Brownian motion. I don't think so. There is nothing Brownian, nothing Gaussian in the limit here. You can describe it in very involved way and in terms of Brownian motion. So everything is somehow encoded in a Brownian motion, but there is nothing Gaussian about the limit.
Just to relate the question you had, why is it the gradient of the GFF that you see stuff, I mean, with this sort of Pierre and Paris and Sabo and Titus stuff by saying, you have a super walkers and the loop that comes from infinity that you have half discovered, and then you are going to discover the final half that has to go way back to infinity, and therefore it's locally stationary, and the pictures have to be like GFF or weighted.
I always had the feeling that what Christophe and Pierre and Titus are doing, Titus is new, I think you are new in that story, so it was Christophe, and that it must be related. And I discussed with Pierre, of course, about this, and also and I couldn't put my finger on it somehow. So that there are some similar flavor-wise, very similar things here, and with the, how do they call it, the vertex range jump process. So certainly there are some relations. I was not able to find them. Thank you.